Hey, you clever little cupcakes. Today we are going to be applying the law of sines in acute triangles. Let's go ahead and start off with what the law of sines is. It's a ratio where the sine of our big A is equal to the sine of big B over little b, which is equal to the sine of big C over little c. And we're going to get a little picture here to help us out. And I'm just going to draw some arbitrary little triangle here. It's not right angle, it's not equilateral, it's just some triangle. And I'm going to label it little a, little b, and little c. And the angles opposite these sides, so opposite little a is big A, and opposite little b is big B, and opposite little c is big C. So the law of sines is just a ratio that says if you take the sine of any angle and divide it by its opposite side, it'll equal the sine of any other angle divided by its opposite side. And even though the law of sines is usually written as three parts, A, B, and C, if you're using it to solve a calculation, you really only need sine of some angle divided by its opposite side is equal to the sine of some other angle divided by its opposite side. You don't need to write out all three. That's not necessary. And one more perk of the law of sines, super cool, super ability, it is flippable. Which means if you're solving for an unknown angle, it works really good to have your law of sines written like this. But if for some reason we have to solve for an unknown side, we can actually flip the law of sines upside down, turning it into A over the sine of A is equal to B over the sine of B, and that will save us some algebra and help us out if we're going to be solving for an unknown side. So let's go ahead and do a little example here. I'm going to scroll that up, and I'm going to draw us a little triangle, keeping in mind that my triangle is just absolutely arbitrary. It's not drawn to scale. 12, 10, theta, and 50 degrees. And sometimes folks ask me what theta is. Theta is just an unknown angle. I could use X, I could use dinosaur with a top hat, that doesn't matter. The only thing that we need to know is, do we have a side and its opposite angle? We do! Because we're solving for an unknown angle, we can write our law of sines as the sine of angle A divided by A is equal to the sine of angle B divided by B. We first find our matching side and angle. So it is the sine of 50 degrees divided by 12, and it will equal the sine of our unknown angle, theta, divided by its opposite side, 10. To get this sine theta all by itself, we are going to need to multiply both sides by 10. That will cause these 10s to divide out, they become 1, and on the other side it will end up leaving us with the sine of theta is equal to 10 sine 50 degrees divided by 12. You can plug that right into your calculator. Mind your brackets though. If you do the top, do 10 sine 50, usually on a graphing calculator, hit enter, then divide by 12. Otherwise, it might try and do it all at once. You want these multiplied up top first. This is going to equal the sine of theta is about 0.6384. Now, that's not your final answer. That's the sine of theta. And if you've done right angle trig before in SOHCAHTOA, you should know how to get rid of this sign, and that's by using the inverse sign. So we will get that theta is equal to the inverse sine of 0.6384, which is going to leave us with theta equals 39.7 degrees. And just like that, we were able to use the law of sines to get an unknown angle for an acute triangle that's not right. Let's go ahead and do another example. Scrolling up, and I'm going to draw another triangle here. Once again, my triangle is totally arbitrary. I do not draw triangles to scale. I never have. I am not likely to start anytime soon. And so I label this one marvelous. And I'm just using little arrows to mark my angles so it's easier to see. So we have an X and we have a 10, and it's 70 degrees and 40 degrees. We are looking for an unknown side. So I would write my law of sines as A over the sine of big A is equal to little b over the sine of big B. This is a time saver. The law of sines is flippable if we're looking for an unknown side. Do we know a side and its opposite angle? We do! I really hope someone out there is like, yes, like when I ask those questions. That would make me giggle with delight, just throwing that out there. We know a matching side. It's the 10 and the 70 degrees. So we can write 10 over sine 70 degrees is equal to x over sine 40 degrees. We want to get this x all by itself. The only way we're going to be able to do that is if we multiply both sides by sine 40. Don't panic about that. We're just going to bring it up to the other side. No different than if it was the number 2. No different than if it was the number 2. We'll squeeze that right in there. Sine of 40 degrees. On this side, they're going to cancel. They divide out to become 1. It leaves us with x equals 10 sine 40 degrees all over sine 70 degrees. You can plug this into your calculator. Make sure you're in degree mode. It's going to leave you with x equals 6.84. And these are unitless triangles. Mind your question if you were given meters or centimeters or anything like that. These ones don't have units, so we don't have units. If you wish to kind of double check your answer, you should know that the larger angle will have the larger side, so the smaller angle has the smaller side. We got a 6.84 versus the 40 degrees. The other side was 10 to 70. That kind of checks out. If you made a mistake and somehow your x worked out to be bigger than 10, that will be a flag because this 40 degrees is smaller, so we needed a smaller side. We're going to do one last example. One last example. Here we go. We're going to draw a triangle once again, and once again it is just going to be some arbitrary, not just, I draw all my triangles exactly the same. Sorry, all my acute triangles are going to look exactly like this, no matter how many times I do them. We get 50 degrees down here, and I'm going to label this one as 60 degrees, and a 10, and an x. All right. We start off by recognizing that we're solving for a side. So we know it's going to be A over sine A is equal to little b over the sine of angle B. And then we're all set to start this, except we realize, uh-oh, we don't know a side and its opposite angle. We can see that this x matches the 50, but this 60 doesn't match any side over here. And this 10 doesn't match any side angle over here. However, because we're all clever little cupcakes here, you can actually solve this angle. Because you have two angles within a triangle, you can get the third one. You know they have to add up to be 180 degrees. So 180 minus the 50 degrees minus the 60 degrees will equal 70. We now know that this angle right here is 70 degrees. Watch those ones. I've seen them show up on assignments and tests where they try and trick you, and you're like, there's no opposite side and angle that match, and there is, because if you have two angles, you always have the third angle. If you have two angles, you always have the third. Now we can go ahead and fill these in because we know a side, 10 divided by the sine of its opposite angle, which is 70 degrees, is going to equal x divided by the sine of its opposite angle, 50 degrees. We want to get rid of this sine 50. We remember how to do that. We're going to multiply both sides by the sine of 50 degrees. We're running out of space on this one. I'll just kind of put that right there. Sine of 50 degrees. On that side, they'll cancel out, divide to become 1. We're left with x equals 10 sine 50 degrees divided by sine of 70 degrees. That can go right into your calculator. Just mind your brackets. Sometimes in a calculator you have to bracket that before you hit divide, and sometimes it'll even put extra little brackets around your 50. That just takes some practice with your calculator. If you've done it correct, your final answer will be 8.15, also unitless because we have a unitless triangle. But just like that, there is 3 examples on how you can be using the law of sines to solve an unknown side or angle in an acute triangle. I hope that was helpful, and I hope to see all you clever little cupcakes next time.